This looks very interesting talk.
Okay, hi. Thanks all for coming to my talk about BLASPhemy. It's a project I've been working on last year during my internship in a Julia lab. And it's about improving Enzyme, an autodiff tool which is quite used in the Julia land nowadays for linear algebra routines, which are obviously used a lot for Julia. So about my collaborators, I started last year.
You have to talk to the microphone, otherwise it's...
Oh, yes, for the online people.
Yes.
Sorry. Yeah, so those are my collaborators since last year. Billy has taken over the project a few months ago. And yeah, the other colleagues obviously also have. Now, for those who don't know so much about AD, that's how AD in most languages looks like. You have source code overloading, source code rewriting. So either, no matter if you have C++, Julia, Rust, or whatever, your tool takes some source code in, produces a new function or some new source code which computes gradients for you, which is great because you don't want to apply the chain rule to large functions yourself, right? That's just error prone. So let software do the job. Now, obviously, all those languages have a compiler backend. In the case of Julia and a lot of other languages, it's LLVM. LLVM is going to optimize your code and generate a binary for you. Pretty great, except now every single language out there has to implement their own AD tool, which isn't that great after all. There's a second issue with that, which I show in this case study, vector normalization. So your compiler implements a lot of optimizations for you. Whatever code you write, that's not what ends up in a binary. So here, let's assume we compute the magnitude. It's a super primitive approach. Let's say we loop over each element and we divide by the magnitude of our vector. Now, computing the magnitude is O of n, looping is O of n, we have O of n squared in total. Obviously, this is pretty naive because our whole input vector is not going to change at all during the whole computation. So it's loop invariant, right? So there's a optimization pass called loop invariant code motion, which does kind of what the name says. It moves invariant computations out of a loop. So now suddenly you have O of n, which is great, right? Now there are some issues if you do source code AD with those cases. Because let's look at this pipeline. We now first apply our loop invariant code motion. We have O of n, we differentiate it. That's under reverse mode AD, which is the most common one. Details don't matter so much, but effectively we rewrite your code. And obviously rewriting your code might introduce some new data dependency. Here everything is fine. You have a simple loop. We rewrite it. It's still a simple loop. Now what happens if we go for source code rewriting? That's effectively the lower half is what all the other AD tools out there do, which work on a source level. So they don't have any optimization passes available because no compiler is optimizing source language. They all optimize intermediate representation. So now you rewrite your source language and suddenly you introduce some new data dependencies for the computation of your magnitude. Now that's pretty bad because now you see dres is something which is computed in the previous step. It's computed based on the loop variable I, so now it's not loop invariant anymore. So that's bad. Now, whatever you do as an optimization pass, you can't really move it out of the loop anymore, right? So here you suddenly end up with O of n squared instead of O of n. So there are a lot more of these optimization passes, but at the end of the day, what Enzyme does is we first let your source language be compiled down to LLVM IR, and from there on we optimize, run AD, and optimize again, just to be sure, before we generate your binary. Now, so yeah, we did run a couple of benchmarks, Enzyme after running optimizations, Enzyme before running optimization against some other tools, and effectively, it's kind of what might be known in the GLN nowadays. Enzyme is quite fast in the majority of cases. So it looks like it's a great start to differentiate some linear libraries, right? But what if that's not true? Do we really want to rewrite linear algebra libraries? Because BLAS, for example, basic linear algebra subroutines are not your average code. That's not what any of us here would write, right, in our day-to-day job. So maybe we should reconsider. For those, let me just give a quick introduction about how BLAS works in Julia land. So you do have a couple of matrix and vector types, and if you do operations on them, generally they are going to get lowered into BLAS calls. So someone else implemented them for you. You don't need to re-implement them. They're quite optimized. They are multi-threaded. If you're lucky, you get an optimized version if you have a supercomputer for specifically your hardware. And I mean, if you look at Intel MKL, for example, that's closed source. So for Enzyme, that's a bit tricky, because if you just give us a binary, some assembly, we don't really know how to differentiate that, right? But we can replace your black box code to some linear algebra library which we understand. So what we do and what we did for a couple of years in Enzyme.jl is every time you load a BLAS library, we just unloaded it and load our own BLAS library. Sorry. So there are a couple of issues, as you can imagine. It might be slower because we always load the same openBLAS version, no matter what supercomputer you have. It's single-threaded because multithreading is complicated. We don't want to deal with that, right? And it works, except when it doesn't. So what issues do we have with correctness? There's GEMV, which means general matrix vector multiplication. It's a super simple thing. You have a matrix and a vector, right? What can go wrong? Apparently a lot, because BLAS routines nowadays have a lot of short path. So if you know that one of your dimensions is 0, you know that you don't really have to do any computations, right? So you return early, which is totally fine for your primal. It's not so much fine if you want to compute gradients, because the way in which those functions get rewritten basically introduce error cases. So that's what we had as an answer back then. We simply removed this optimization from our BLAS library. So it's not only we gave you a generic library, single-threaded, which is slow, we also went ahead and removed some of the optimizations from that BLAS library. So you can imagine how fast that ended up being, right? Yeah, we were at least honest about it. You got a couple of these issues every time you try to differentiate a BLAS routine using Enzyme. And as a result, obviously, people created issues about, hey, surprisingly, or not surprisingly, Enzyme.jl is slow in BLAS. What can we do about it? We did some benchmarking also. Pretty much as you expect, if you have a single-threaded BLAS library, it doesn't really benefit from your multi-thread environment, which is also sad. So yeah, let's think about, do we really want to differentiate BLAS routines? I mean, Enzyme is cool because it is able to do that. It's the only AD tool out there, which we have for Julia, which can differentiate BLAS routines. But apparently, we might reconsider that, right? So let's try on a higher level set. So if you look at BLAS routines, actually, that's, for example, the matrix vector. It has like 12 different arguments, where on the Julia land you might have only 2 types, right? So differentiating defining gradients for 2 arguments is easy. For 12, it's not so much fun anymore. So maybe we want to go a level higher, right? Enzyme has its own set of custom derivatives, like you have a chain rule ecosystem. Enzyme is a bit specific. It wants its own enzyme rules. But at the end of the day, you can define it on a higher level in Julia itself, which is nice. So thanks to the Exen who went ahead and added some extra rules, that's the most simple function. Dot is literally like take 2 vectors, multiply, and add them up. So how much faster can it be? Apparently a lot. So that already, like, it's the most simple function. Even there, we kind of screwed up before performance-wise. So that shows how important those rules are. Obviously, now that we have Julia level rules, we are wondering, like, can we go even better? Can we get some compiler internal rules which give us even better performance? Which is a route which took us a lot of time afterwards, because yes, we can write compiler internal rules. That's called tablegen. It's an LLVM-based tooling which allows you to do code generation, which is great for such simple cases. For large functions, it's a trap, because you can define your custom derivatives, but like that's what you end up with. So it's still a lot better than whatever we had before, because if you try to actually write the code out by hand, which differentiates BLAS, like matrix-matrix multiplication, for example, it's over 1,000 lines of code. And BLAS doesn't only have 1 function, it has like 20, 30, and then you look at Lapack and you're completely lost. So we do need some tooling. It is great, it's still not super readable, so there are unfortunately not that many people yet who contributed Enzyme core AD rules, but it's at least making progress. The question now, was that really worth it? And yeah, I mean, one of the things which we see, if we actually stop replacing your optimized BLAS library with a single-threaded generic library, we do get multi-thread speedups, which is great. We do also get a couple of performance improvements over competitors. For example, in comparison to Cyrus, I don't have numbers before. I think we are pretty slow. Now we are on average maybe like 2 times fast on a single-threaded version. The multi-thread version was a bit awkward while benchmarking, but those numbers are also pretty old, so hopefully we improved a bit since. But yeah, there are also correctness challenges, because first we want to test all of these rules, of course, in CI. Now, what do we do with, for example, QBLAS? It's just another BLAS library at the end of the day, but we don't always have an NVIDIA GPU in CI, right? Same with all those different libraries. There's openBLAS, there's Intel MKA, there are so many different variants. Some are written in C, some are written in Fortran, and even if you have a Fortran library, it might not behave the same as another Fortran library, because depending on your compiler, the ABIs are completely different. It's a mess. Writing manual tests is also not really sustainable, because on a high level, yes, you can test your Julia rules for BLAS routines, because you have 2 input arguments, right? How complex can it be? as you've seen on the lower level, BLAS routines actually have like 12, 15, maybe 20 input arguments. And each of those is, for example, transpose. So like, what if you flip one of your matrices? If you have a diagonal matrix, you have the upper diagonal, lower diagonal, what's triagonal, yeah. So they're just a combinatorial explosion of steps. We don't really want to write them by hand because we tried that, we didn't got far. People complained about incorrect results, which obviously isn't great if you want people to use your tool, right? So what we did is we did some kind of symbolic testing. So we had fake versions of our BLAS calls. So our own implementation, which instead of computing any outputs or so, we don't care about outputs. We just had a kind of global stack. And so every time you call the BLAS routine, that BLAS routine pushed something on the stack saying like, hey, I'm a dot call, or I'm a matrix vector call. And I have those 12, 15, whatever arguments in that order. And then it's just getting saved. Now the funny thing is, if you differentiate such routines using Enzyme, Enzyme is going to recognize the name because we match obviously whatever BLAS routines out there use as a naming convention. So Enzyme is going to introduce new BLAS calls, which then again, if you look at the implementation, are still fake implementations. So the derivatives which we implement will also push their name and their arguments onto a stack. So once we differentiate the function, a fake BLAS function, and we look at our stack after running, we see only like, hey, I'm a dot call, I'm a XP call, I'm a XP call, which is like scalar times vector. And yeah, so now we can check our inputs to each of those calls. We don't see the actual outputs because those are a bit complex to test, but we can automate those types of testing. And we did catch a couple of bugs. Now we are able to test at least QBLAS also in CI. And yeah, that's obviously pretty nice. Let's see. Yeah, so what's our final performance? Oops, wrong slide, sorry. Yeah, so our linear algebra routines with Enzyme now have a couple of improvements. We have around 5,000 lines of logic, which we wrote in order to like automate all those code generation thingies. We have around 60, 70,000 lines of code. That's only for the first, let's say, 10, 12 functions. So we do hope once we add the remaining functions, the numbers of generated lines go a lot up without any of the logic having to change. And yeah, we do have a lot of features. For those, I mostly have to give a shout out to Billy, since I implemented the basic logic reverse mode and some testing, and he added like all those fancy new things. So for example, we now have runtime activity, which in Enzyme world means I'm at compile time not really sure if I want to have a gradient for that, so just be aware I might ask you later for it. It has a small runtime overhead, because we do need to cache a couple of things, but now that means later, like during runtime, you can say like, oh, actually, give me the gradient, in which case, yes, we give it to you, it has a small overhead. Well, you can also say, I don't need any gradients at runtime, which means, well, there won't be any like gradient computations. It still has a small runtime overhead because we cache things in the forward pass, but it's pretty small compared to computing gradients at all. We do have batch mode as a new feature. I'm not sure about how many other tools are there which currently support that. I think it's a bit work in progress. We do have QBLAS support. It's pretty new, so please feel free to test it. And yeah, the functions on the BLAS side, these are the ones which we support. So it's the basic ones like vector-vector product, scaling a vector by a scalar, matrix vector, sparse matrix vector, general matrix matrix. And the second line is a couple of solvers. So yeah, some decompositions. We do have our symbolic verification system, and thanks to an external contributor, we also have a couple of tests, like normal tests, to make sure that our symbolic verification system is also working. And yeah, so now that we have all those things, can we look a bit more into the performance? Like we've shown we are approximately 2 times faster than Zygote, right? But we've seen there were a couple of awkward drops around here. So what can we do? Asking our profiler. And there was some interesting insights if you look at the performance results, because generally if you have computations like matrix-matrix, you do expect that actually there's some work to be done. It's not only copying elements around, it's also like some pure math. But if you look at what VTune tells us here, approximately 70% is just a mem copy, which seems a bit awkward. So our assumption is that enzymes, despite being like already 2 times faster than Zygote, still has some internal bugs. Probably, maybe we got some bounds wrong or so, so we are caching more than necessary. So that's something we want to look into, because obviously if we can strip those 70% down to, let's say, 40, to make up some numbers, then we'd be even faster, right? Makes sense. Yeah, so that's a bit awkward. We also have some benchmarks against C, because, I mean, Julia often enough claims to want to solve the two-language problem, right? So now that we have our compiler-based, tablegen-based rules, we can suddenly also support C, which we didn't have any fallback for C before. So Julia was in the past actually the only enzyme front-end which supported BLAS routines. Now with those rules, we also have C support and all other languages. And I mean, one thing we see is like first for the primal, which means the original function, which just is based on some, I think, matrix vector multiplications. Enzyme, like the primals are all pretty much the same. So Julia, C, whatever, it's close, right? Now, if you look at the results where we differentiate things, suddenly things become a bit worse for Julia. So Julia is for some reason slow, and once you look into the like matrix implementation, you also see why. So in CLand, everything is pretty simple. You call malloc, calloc, whatever, and you get some allocation. You have a pointer to it, and you pass those pointers to BLAS. It's a pain because you've seen like how many arguments you actually have. It's like 12 different ones. You never get them right. So you hopefully use some library like Eigen, which makes it a bit nicer. It's still a pain. On Julia instead, you have your nice objects, matrix objects, which like as your variable first is a pointer, but then your matrix is also a pointer, so you suddenly end up with a double pointer, which for Enzyme is bad, because if you have a single pointer, we can observe, like, are you writing into your matrix? Are you overwriting some elements? Well, we might need to cache them, because for the reverse pass, we need the original input to compute correct gradients. So we might cache it. But if you have double pointers, that's kind of a lost game. So we don't know if you write into like your outer pointer, like where do those inner pointers point to? Do any of your matrices overlap? Do your vectors overlap? To some extent, that's allowed. So we need to be conservative, which in the worst case means if you have a like BLAS routine which has 5 input matrices and vectors and you overwrite one of them, we need to cache all 5, which is obviously terrible and which could to some extent explain why we are mem copying so much. And yeah.
Have you checked whether fixed sized arrays fixes this? Because that will fix that doesn't have the double pointer interaction.
Is that the memory-based one?
Yeah.
Yeah, we're waiting for that. As far as I know, last time I talked to Billy, we don't support 1.11-ish.
Okay.
So we are waiting, and yes, that's what we're going to do. Which is also why we didn't investigate on the enzyme side, because we hope the problem is going to solve itself. Yeah, so do you have any questions on like any of the performance aspects or any of the future development? No? So I have 2 more extra slides, but
Okay.
yeah.
Keep the questions at the end.
Okay, yeah. So yeah, one project which I've been working on last year after implementing like some of those derivatives rules are optimization, because I like working on LLVM, as you might be able to tell, and LLVM has all those fancy optimization paths, right? The issue with that is they're pretty low level. Like I showed one example, which is loop invariant code motion. There are a lot more of these. They are pretty low level. So they don't really understand your math. Like if you have matrix objects, I mean, at the end of the day, for a compiler, it's just a pointer. Or in the case of Julia, it's a double pointer. It's not, there isn't really a concept of a matrix. Unless you go for some higher level compilers like XLA, MLIR, whatever, they might be able to do it, not so much on LLVM itself. So what I did is first, a simple one was BLAS GemV, which is matrix vector. Now if you have a couple of matrix vector products and you do know all of your vectors are consecutive in memory, or at least they have the same distance to each other, then you can merge it. Because like the general matrix call literally has one thing which is called increment y, which says like, hey, how much space is there between your different columns of your second matrix? So you could merge them if you know a little bit about your inputs. And in the case of batch mode, we might do that in some cases. So technically, this one would be a lot faster, because I mean that's technically what's already happening for a batch size of 4. We want to merge them. There are a few more of these optimizations, which, like if you have outer products, inner products, there are some cases where you don't need intermediate results. So just by matching on those names, you can recognize some of the intermediates being useless and just effectively throw away whatever BLAS combinations the user used and insert a smarter row of BLAS calls. That's something I worked on. I never really finished. Nowadays, we are also not 100% sure if that's the right approach, because first, there are some higher level optimizations. There are polyhedral optimizations, which have some understanding of math. And for example, if you look at the Enzyme AD repository nowadays, there's Reactant, I think it's called, .jl, which tries also to compile everything through MLIR, which has already all the infrastructure. So we don't really need to rewrite all those optimization passes if we use MLIR instead of LLVM. Yeah. Okay. Yeah.
Last one.
Sorry?
Is this the last slide?
Yeah.
Oh,
Yeah.
okay. Then
Yeah.
please thank our speaker first.
So now we have a question round. So
Yes.
anybody has a question?
Yeah.
Yep.
Maybe just a quick question about the, you just mentioned like the reactant and MLER story. I was wondering to what extent you were seeing like the future of enzyme, like going with for matrix operation, going to the MLER route or the optimization you're kind of discussing?
I mean, I'm not the one working on the MLIR side, so I only can give you second-hand information. But yeah, so for high-level optimizations, it's generally nice to have a higher-level dialect, which MLIR offers. So I do know they want to use, I think, mostly for ML tools, because for ML you have all those large tensor objects. You don't really have like really nitty, like small math for loops or so. So that should be a lot faster. If you ask Valentin, he tried before to use MLIR in Julia. The issue is back then, it's called Brutus, I think. So what he did is effectively replace the LLVM backend of Julia and just insert an MLIR backend. The only issue is if you go for the Julia intermediate representation, that's already pretty low level. So at that point, you already lost your information, like, hey, that's a matrix object. So then you need to try to regenerate all that information. It takes a lot of compile time, and usually you don't really get much performance out of it. So now the new one, Reactant, starts pretty high level. I don't know, do you know more about it? Fair enough. But yeah, it starts pretty low, high level, so hopefully they get some more performance out of it. Yeah.
Any other questions? I have one question myself. So I wonder if you can just, given the talk yesterday from Jeff, if you already can think that whether this code can be fully statically compiled. It seems that you're still using some runtime niceties.
I mean, the runtime activity, you mean? That's not really something which should matter for the compilation process. It's just we have both paths available and we cache a little bit more, but it shouldn't hinder static compilation. I do know Enzyme has a pretty unique compilation pipeline in the Julia ecosystem because it's based on GPU-compiler.jl. I'm not so much of a Julia compilation expert. I mostly work on the backend, so I can't tell if there's anything which blocks pre-compilation, unfortunately.
Okay,
Yeah.
no, but if it works with that, maybe I'm pretty sure it
Yeah.
will go with static, but make sure that it will be statically compiled so that
Yeah.
other people can just deploy in HPC and other.
Yeah, that would be pretty nice, of course.
Okay.
Yes.
Do you have more question? Another question?
So from the Julia compiler side, I think Valentin's talk on making GPU compiler pre-compilable with specialized caching, I think should mean that as of whenever Enzyme gets Julia 1.11, I think, maybe 1.12, somewhere in there support. It should become pre-compilable and therefore statically compilable eventually, but do not take this as gospel.
Okay.
Okay, thanks for that remark.
Okay, so we get all the nice things at one, like our memory types and the pre-compilation, hopefully.
Yeah, hopefully.
So yeah, then in that case, we just need to wait a little longer.
Okay, oh, that sounds great. Okay,
Yeah.
more questions? If not, then I would like to thank our speaker.